Welcome to part 2 of how to answer the energy calculations. Once again, if you've not done so already, check the link underneath this for the free download of this booklet. Have a go at the questions first before we go through the answers. So question 7 here has got points that it wants you to look at the kinetic energy of the diver. It gives you that energy of 5040 and it gives you some speed, and we've got to calculate the mass. So as before, let's write down our equation of what we've got to know. So we want the kinetic energy here, which is half times mass times velocity squared. We then want to insert the values that we know. So we know the energy in this occasion is 5040. Half is 0.5. We want to calculate the mass, which we're not sure of, and we have the velocity of 12, so that's going to be squared. Once we've done that, we can then rearrange this calculation to make mass the subject, and we do that as follows. It's energy divided by half times the 12 squared. And that will give us an answer of, we should plug that into our calculator, of 70 kilograms. So the 3 marks here, 1 for the correct answer, 1 for the substitution, and then 1 for the rearrangement. Question 8 wants you to calculate the efficiency of the electric motor. So efficiency is useful energy divided by the total amount of energy. So our useful energy here, it says it transfers 35,000 joules of useful energy each second, and it also tells us that it has an input energy of 50,000. So our useful energy is going to be 35,000, and then we divide that by our 50,000. Remember, for efficiency, it must be under 1 or 100% when we times it by 100. So in this case here, it's just 2 marks. So you get 1 for doing the calculation. That will come out at either 0.7 or 70%. Remember, do not write 0.7%. And we've got here, determine the spring constant of the spring. So the calculation you want to use for this one is the force equals the spring constant times the extension. So what we want to do is find a nice little point on our graph where we can look at the force and we can look at the extension. So I'm going to choose here 4 newtons, and then this point here, it goes down, is going to be at 0.1. So they're the figures that I'm going to be using. You can have any point on this gradient. So the force here is going to be 4. We want to work out the spring constant, so we're not sure what that is, but it's times the extension. And we can then rearrange that. So our spring constant equals force divided by extension, which gives us an answer of 40 Newton meters. This one wants us to calculate the elastic potential energy. So just highlight here. And then we can highlight what things that we have. Now we have the extension of the spring of 20 centimeters. We've also been given the spring constant of 13 Newton meters. So what calculation do we want to use? Well, we want to use the elastic potential energy, which is going to be half times the spring constant times the extension squared. So let's have a quick look at this equation here. So we want to calculate this energy, so we don't know that. So we've got half here times K, the spring constant. That's going to be 13 Newton meters times the extension squared. Now, if we notice for the extension, we've got here it being 20 centimeters. Now, this needs to be in meters. So when we rearrange that, we've got 0.2 meters. 20 centimeters is 0.2 meters. And when that goes into our calculation, our calculator, we should get 0.026 joules. Another efficiency question here. Remember, we just said it's useful divided by total. The useful is going to be 360 divided by 750. It's exactly what you do in a test. You know, if you got 20 out of 100 in your test, that is going to be your useful, and that is going to be your total. It's the same process here. Our useful is 360 watts, and our total is 750 watts. When we divide that, it comes out at 0.48 or 48%. Either one is acceptable. Question 11 here, it says about both types of balls produce the same power output. Calculate the useful power output of the CFL. So here's the CFL. Oops. Alright, so what have we got here? Well, we've been given our power input. So that's what goes in, and we've been given our efficiency. So our efficiency equals useful divided by our total. So when we look at our calculation here, we want to basically rearrange this, and we want to find out what's going in. So we want to work out what is 20% of 8 watts for this equation here, which equals 1.6. So that's going to be 1.6 watts. And then we can test that in our calculation. 1.6 divided by 8, alright, should be 0.2. Then we've got to calculate the efficiency of the LED bulb. So the LED bulb is that one, but we've also been given the information is that they produce the same power output. So when we look at this calculation, we want 1.6, right, because that's our answer back here. And we've been told the power input is 5, and we divide that by 5, which gives us an answer of 0.32, or if you times that by 100, we've got 32%. Next question also wants us to calculate the efficiency. It tells us here that the total power is going to be 600 and our useful is 540. So 540 divided by 600 is 0.9 or 90%. Again, either or is acceptable. Our wasted energy here, how much power is wasted? Well, if the total is going to be 600 going in, 540 is useful. What does that leave? Well, it leaves 60 megawatts. Remember, mega is million. Calculate the energy wasted by the light bulb in this period of time. So what is the time it's referring to? Here, there's a certain period of time when we've got a 30 watt light bulb that uses 600 joules of energy. So what calculation might we want to look at first for this one? Let's have a little look. So we've got 600 joules here, and it tells us we've got 450 joules of light energy. So our wasted energy in joules, if we've got 450 of light energy, that terminology we have to be careful with. That's what I was just thinking about then, because it's obviously we've changed our idea about energy since this was published, so don't get confused by that. But we've got 600, take away 450, and so our wasted energy is going to be 150 joules. And then we want to calculate the efficiency, so that's going to be 450 divided by 600, 0.75 or 75%, just like the other ones that we've just done. And calculate then the time period in seconds during which the 600 joules is provided to the 30 watt light bulb. So power equals energy over time. What information are we given here? Well, we're given the power. That's 300 watts. What else information do we have? Well, we're told that it's 600 joules. And then we want to work out the time period there. So when we want to rearrange this, time equals 600 divided by 30, which will give us an answer of 20 seconds. I'm going to stop this here. Stay tuned for part 3. I hope this helps so far. Again, you find the booklet in the link.